All right, so we did translations last week. There are going to be a few more complicated translations in the homework this week, but you have what you need to do all of those. It's just a matter of applying the rules we learned for conditionals in the simple cases, breaking the complex sentence down into components, and thinking carefully about where the if is, where the only if is, what's a necessary condition, what's a sufficient condition, and your translation should track all of that. And we're going to talk a little bit more about more complex cases if you're puzzled by any of those translation problems at the beginning of next class. For now, though, we're going to go ahead and talk about our first inference rules in sentential logic, which are going to be pretty foundational to a lot of the rest of what we'll be doing through the semester. These inference rules only involve negation or tilde and conditional or arrow. And there's obviously going to be a lot more inference rules that we'll learn when we are introduced to the other three logical connectives later. And then we'll talk about direct derivations, and I'll go through how to do those on Carnap. Okay, so the way to think about inference rules is that they're really just valid argument forms. And we're treating them as rules because what they tell us is that certain sentences in sentential logic validly follow from some other sentences in the logic. Or an argument that had those sentences as a premise and as a conclusion would be a valid argument. And one of the things we learned when we worked through the introductory material was that formal validity has this quality of generality. So if you have an argument form that you know is valid, that's a formally valid argument form, then you know that every instance of that argument form is also valid, every particular instance of that argument form. And that's what allows valid argument forms to function as general rules. So wherever you see an argument of a particular form appearing, you know that argument is valid. It also means that if you only get the premises of that argument, or an instance of the premises of that argument, you know that you can validly infer an instance of the conclusion as well. And that feature of validity is what allows us to select a certain number of valid argument forms that are useful and use them as laws, basically, laws of our logic. And you could, in principle, treat any valid argument form as a rule, but some of them are just more useful than others. So to sort of contradict exactly what I just said, repetition is maybe the least useful of the various argument forms. We will later, in more complex derivations, there will be occasion to use repetition. But repetition says that if you have a sentence of the form box in sentential logic, trivially you can validly infer therefore box. So it's exactly what it seems like. So one thing to keep in mind about all of these as we go is that box and circle and triangle are metavariables. So we can swap in atomic sentences for these metavariables, or we could swap in molecular symbolic sentences for these variables. As long as it's a well-formed sentence in the language, we can let that be the value of these variables. So, for example, if you have P, you can conclude that P and cite repetition. If you have Q, you can conclude that Q, cite repetition. But you also could use repetition to conclude, you can also apply repetition to something more complex, like this conditional that has P as its antecedent and not R as its consequent, or if P then not R, you can cite repetition and conclude, therefore, if P then not R, for any well-formed sentence. And this one doesn't need much by way of explanation, I think. I mean, if you think about what validity is, our definition necessarily, if the premises are true, then the conclusion is also true. So, of course, where the premise is P and the conclusion is P, if the premise is true, then the conclusion is also true. If P is true, then so is P, because P just is P. So that's the sort of underlying reasoning for repetition. It's an interesting question. Those of you who are philosophy majors have encountered question-begging arguments before, circular arguments. Does that sound familiar? This is something that philosophers like to accuse each other of, and I think happens maybe less frequently than philosophers think. But it does happen sometimes. People give an argument for a conclusion that either the premise itself explicitly or implicitly presupposes the conclusion somehow. And it's an interesting question, what exactly goes wrong with circular arguments? One diagnosis is it's not actually the logic. Like, logically, circular arguments are valid because repetition is a valid argument form. It's something else. It's something about what one is allowed to presuppose given the rules of a conversation. And that isn't strictly speaking about just the logic of the arguments. So that's just like something interesting to think about, how repetition may or may not be consistent with our standards for non-circular arguments. Probably one of the most famous, you may have encountered this one, modus ponens. So modus ponens has the form, if you have a conditional on a line of the form if box, then circle. And then on another line, you also have box. You can conclude that circle for any value of box and circle. So paradigmatically, P's and Q's. If P, then Q, P, therefore Q. This, again, makes sense given what we know about the meaning of the arrow, right? The arrow says that the antecedent is sufficient for the consequent. So if you know that P is sufficient for Q, and you know that P is true, then you're guaranteed Q is also true. And that's why that arguments of that form are valid. And again, this can get as complex as you please. So here, box is itself a conditional in this argument form, or in this specific instance of the argument form. So we've got, this is a conditional that has another conditional as its antecedent, and that has a negated simple consequent. So if it's, let's see, how am I going to say this? If it's the case that if R then Q, then not S. It is the case that if R then Q, therefore not S. Watch out for this, because sometimes when you're first starting and you're having trouble picking out what is an antecedent and what is a consequent, don't always go looking for simple antecedents and simple consequents. Sometimes you can apply the modus ponens rule even when you've got this, a whole conditional sitting there on a line. You might not immediately think, oh, modus ponens, but look back up to what you have above in your derivations, and this can itself function as the antecedent of a conditional, and if you have those two, then you can run a modus ponens inference and get that conclusion. So, I mean, intuitively, right, this makes sense that this is valid. If Copper gets a bath, then he howls. Copper gets a bath. So what do you know? Therefore, Copper howls. Right. You know that he's getting a bath suffices for his howling. You know that he's getting a bath, so even if you can't hear it, you know he's howling. And if he's not, then that conditional must not have been true, right? It must not have actually been true that if Copper gets a bath, then he howls. So if you have the true conditional, you have its antecedent, you can conclude it's consequent. I love modus tollens. I don't know why, just always have. Like it a lot better than modus ponens. It just feels right to me. If box, then circle, it's not the case that circle. What can you conclude? Therefore what? Therefore not box. How come? How can we infer that? Why does that follow?
Circle is a necessary condition for box, so if it's not circle, then...
Yeah, nice. Yeah, it's a good way to put it. Circle is a necessary condition for box, or it's not possible for box to occur without circle also occurring. So if you look around and you don't see circle, you know that box didn't occur or isn't true. So if P, then Q, not Q, therefore not P. And both modus ponens and modus tollens, as we'll see in a minute, have fallacious counterparts. So don't confuse these with those fallacious counterparts, which we'll get to in a minute. Once again, keep in mind that complexity can make these harder to spot initially. But here what we have is, if it's not the case that U, then it's not the case that S is your conditional. And your conditional has a negated consequent. And the negation of a negated consequent is a double negation. So you have double tilde S. It's not the case that not S. And if you have it's not the case that not S, and you have that negated consequent, you can conclude that it's not the case that not antecedent, or it's not the case that not U. If you just had S here, you would need to first apply the rule that we're going to learn in next, double negation, before you could apply modus tollens. So there are some systems that don't require you to do that, and the double negation step can be kind of irritating, but this system is sort of maximally demanding in its precision. So in order to apply modus tollens to a negated consequent, if you have a doubly negated version of the consequent sitting there, you can apply it. But if you have something completely unnegated, you need to get the double negation first before you can run the modus tollens. So here's an instance of it. If Copper gets a bath, then he howls. Copper does not howl, therefore what follows? Houston?
He didn't get a bath.
Yeah, he's not getting a bath. If you are not just not hearing him, but sure he actually is not, and you know it's true that his getting a bath is sufficient for his howling, well, he must not be getting a bath. Double negation, kind of like repetition, and it's almost like so obvious. It's tempting to over-explain it, which can make it more confusing, but it just is as simple as it seems. If you have box, you can conclude it's not the case that not box. And if you look back at the truth table for negation, you can see the basis for double negation, right? If box is true, then tilde box is false. And so you can conclude tilde box. That's how you get double negation. You can go from box to doubly negated box, citing double negation. You can also go from doubly negated box to just box, or remove the double negations, and you'll cite the same rule going in either direction. Both of them are applications of double negation, and it just depends, as we'll see when we start doing derivations, like which direction you want to go. is totally up to you, and it just depends on what you think you're going to need in order to proceed with your derivation. Sometimes you need to add tildes in order to run another inference. Sometimes you need to remove them, and it's mostly about sort of planning ahead to see what you're going to need to do, and some trial and error. So there's your instance of it with P. So from P, you can conclude it's not the case that not P. From it's not the case that not P, you can conclude that P. Likewise for Q, for P and Q for any well-formed sentence in the language. So if this were the introductory logic class, or a course on like critical thinking and reasoning, we would spend more time on fallacies. Occasionally we will mention fallacies, but a lot of fallacies, which are bad forms of reasoning basically, occur in the context of non-deductive arguments. And so if you've heard of like the ad hominem fallacy or something like that, that tends to not appear in the context of deductive argumentation. But there can be deductive arguments that are bad forms of reasoning or that are invalid. And in order to be a fallacy, it's not just an invalid argument. Because the silly argument I started with in class was the Wake Forest is in Indiana, therefore God does not exist, or whatever, or there's no free will. Some argument that just is obviously fallacious, is obviously invalid, doesn't count as fallacious. A fallacy has this combination of being both invalid but appearing to be valid. So it has this like illusory quality to it. It kind of sucks you in and makes you think that looks like it should be a valid inference, but it really isn't. And that's what a fallacy is. So affirming the consequent is our first one. It's easy to at first think that, well, if modus ponens works, then affirming the consequent works. Modus ponens is if box, then circle, box, therefore circle. And affirming the consequent starts the same with the conditional, if box, then circle. But instead of being given the antecedent and concluding the consequent, someone engaged in this form of reasoning is given the consequent and tries to infer the antecedent. And you can't do that. That's invalid. So don't confuse modus ponens with this. The antecedent suffices for the consequent. Sometimes the consequent suffices for the antecedent too. When we get to biconditional, we'll see that in some cases, if you're given a biconditional, you can conclude necessary and sufficient conditions for one another. But you don't know right away, if all you know is if box, then circle, whether or not circle is merely necessary for box or circle is also sufficient for box. You need to be given a separate claim. And if you don't have it, you can't infer from the fact that circle that box. So here's how this works in a specific instance. If P then Q, if you're given the Q, you can't infer anything actually. I mean, you can slap some negations on the Q, you can repeat Q, you can repeat the conditional, you can put negations on the conditional and take them off. But that's about it. You can't infer that P. And it's pretty easy to see why, right? So if you have an argument like this, and this is where using a slightly different example than the one on the handout. If it's snowing, then it's below 32 degrees Fahrenheit. That's true, right? It's below 32 degrees Fahrenheit. I think right now that's actually false, but that was true earlier today, right? It's below 32 degrees Fahrenheit. it would be obviously silly to conclude from that alone, therefore, it's snowing. Why? I mean, we can agree that yes, if it's snowing, that guarantees that the temperature is below 32, and also agree that it is indeed below 32, but there may not be snow, because it's being below 32 may not suffice for it snowing. Often it is very cold but no snow on the ground because there's no precipitation. Yeah, no water that's freezing. So that would be an instance of affirming the consequent. Denying the antecedent looks a little bit like modus tollens, but it's not, and that's part of why it's a fallacy. It's this kind of illusion of validity. So it starts the same, if box then circle, and then you might, instead of being given not circle, you might have not box, or it's not the case that the antecedent is true on a line. And the temptation is to conclude, well, therefore not circle, because if the thing before the arrow isn't there, then the thing after the arrow can't be there either. And while that's tempting, it's a fallacious form of reasoning, because all we know is that box is sufficient for circle, but there might very well be other things that are sufficient for circle. Maybe triangle is sufficient for circle too. And so if you know that box isn't around, maybe circle isn't around, but maybe triangle's around, and so circle is too. So here's an instance of the fallacy. Again, if it's snowing, then it's below 32 degrees Fahrenheit. True, but it's not snowing. This morning I looked out and I was like, oh, no snow. I obviously couldn't conclude from that information alone, well, I guess it's not below 32 degrees. Sometimes it is below 32 degrees and there's no snow on the ground. Okay, so we're going to now sort of put these to work, these rules. Any questions about those? I just picked this. Philosophy majors, this may look familiar, or a version of this. This is a version of the argument from evil, which is an argument against the existence of God. And, you know, this is not a direct quote from anyone, but you might encounter something kind of like this in a philosophy text at some point. And what we're going to do is we're going to just quickly turn this into a sentential logic argument. So we're going to translate the argument sentence by sentence. And I'm going to tell you in advance this is logically valid, but it's complicated. There's a lot going on. And our methods that we had from the introduction of proving validity or invalidity they worked for a certain limited number of arguments, relatively simple ones, but the more complex you get, you may not be able to apply the thought experiment method, both because our brains just can't quite do that with additional complexity, and because with something like God, if God exists, then God exists necessarily, at least according to like classical theism. And so possibility and necessity becomes really difficult. Like, consider a world in which God doesn't exist. Well, like, if God exists, there is no such world, at least according to theism. So when you're dealing with matters that are themselves intrinsically necessary, methods of thought experiments often just break down. And the hybrid method that makes use of formal validity is sometimes useful, but when you've got like a bunch of steps, it's more useful to just turn to something completely formal. Okay, so I'm just going to read the English. if God exists, then God is omnipotent, omniscient, and omnibenevolent. Sometimes called the tri-omni-God. This is the God of classical theism. Omnipotence means all-powerful, can do anything. Omniscience means knows everything, for every truth, past, present, and future. An omniscient being knows that truth. And omnibenevolent just means all loving or all good, perfectly good, right? So the first premise just tells us, if God exists, here's what God is like. God can do anything, God knows everything, and God is perfectly good and all loving. Second sentence says, God is omnipotent, omniscient, and omnibenevolent. That is, God has those features only if God eliminates every evil. And evil is just like pain and suffering. And the thought is like a being that was all-powerful would be able to eliminate any evil, any suffering. A being that knew about that suffering would not just be able to eliminate it, but would know exactly how to go about doing it. And a being that was perfectly good would want to. Like a perfectly good parent certainly doesn't want to see their child suffering, and definitely doesn't want their child to suffer terribly and then die a brutal death, which does happen, of course. And if they could stop it, of course they would. It's the thought. So if this is what God is like, then God should get rid of all that suffering. Third sentence, God's eliminating every evil is sufficient for there being no evil. That's like if an omnipotent being really does eliminate all the suffering, then there isn't any, because they did it successfully. An omnipotent being doesn't like try and then trip over their shoelaces and like, whoops, I tried to get rid of the evil, but I screwed it up. Nope, that's not the way a being like this works. We look around, though, there is suffering, there is evil. Therefore, God does not exist. You can see this argument unfolds in kind of logic, a series of if-thens, and then we get hit at the end with the there is evil, and the conclusion falls out of the antecedent of the very first conditional, God doesn't exist. So let's get started by just representing God exists as P. So we'll then represent God is omnipotent, omniscient, and omnibenevolent as Q. God eliminates every evil as R, and there is evil as S. And then we can just like swap out P, Q, R, and S for those sentences in the right places. And here's what we get. If P, then Q. If Q, then R. If R, then not S. But S, therefore not P. This looks like it should be valid, right? You can kind of like start to trace it, because if you've got if P then Q, and you've got if Q then R, we haven't learned this rule yet, but what seems to follow from those two? If P then Q and if Q then R, just those two, what can you conclude?
If P then R.
Yeah, if P then R, a kind of transitivity rule, right? And then you've got if R then not S. Now pair that with what you just inferred, if P then R. Now what can you conclude? If P then R, if R then not S.
If P then not S.
If P then not S. Now we've got S. Apply our double negation rule. And what do we get? Not S. Got write it up. Not S. And we've got if P then not S. And if we apply modus tollens, what are we going to get as our conclusion?
Not P.
Therefore, not P. Right, so just based on like knowing those rules and also just kind of common sense, you can start to see this is definitely valid. And we just did actually some of what's going to happen in the derivation. But the direct derivation is a method of formally proving in a step-by-step method that in each step cites established rules that proves that not P really does follow from those premises validly. So it's particularly useful if you've got a complex argument that you know is valid and it doesn't adhere, obviously, to any simple argument form. You could also use it in principle to test to see whether an argument is valid, even if you don't know in advance. We'll be using derivations mostly with arguments we already know are valid. And that little symbol there, called the turnstile, sometimes called, or the meaning of it is syntactic consequence. You can think of it as a therefore. Essentially, what that symbol means is those sentences which are separated by commas, as a matter of their form and the logical rules, that are sort of background assumptions, imply or entail that sentence. There's also a notion of semantic consequence, which we're not going to fiddle too much with, but when we get to models, part of what truth tables are doing is giving us a notion of semantic consequence. You can think of it as a therefore, and that does the trick. So you're going to start seeing the turnstile, and you'll also start seeing premises separated by commas and laid out in a row like that on one line, as opposed to listed stacked on top of each other, which I think visually that's a little easier. But going forward in the book, on Carnap, and in a lot of the problems, you'll be given premises as sentences separated by commas, turnstile representing syntactic consequence or validly implies, and the conclusion will be on the other side of the turnstile. And what you'll be asked is to construct a derivation that validates that those sentences really do syntactically imply that sentence on the right. And that's just another way of saying prove that that conclusion really does validly follow from those premises in a particular rigorous way. So we're going to learn three and a half forms of derivation. This is the simplest one, really straightforward, but you'll need to sort of master this method in order for the next one to make sense, and the one after that. Also, you need to understand this one to understand indirect derivation. In every case, all 3.5 kinds of derivations we'll learn, they all start the same way. When you're asked, construct a derivation that validates this argument, the first thing you're going to do is just write the number 1 just to signal this is the first line of my proof, and write the word show and a colon. And the show line is basically announcing, like, I shall now show this. And so the content of the show line that comes after the colon is always the conclusion. And it's a little weird at first, because now suddenly we have the conclusion as the first step. But keep in mind that the reason we're doing that is that we're trying to show that this conclusion follows from these premises. So we start with our show line, put the conclusion as the content of the show line, and we're not just trying to prove that conclusion from nothing, or like ex nihilo, or from some random sentences. We're trying to prove that it follows from some sentences that are very specific, that are the premises of an argument, and namely the ones that are provided for us. So what we do next, after we've done our show line, is we start, I'm going to sometimes put it this way, pulling down the premises from the argument. Now, as we'll see when we get to later kinds of derivations, you actually have some latitude with what order you pull the premises down in, and sometimes you won't pull them all down right away. Sometimes you'll pull one premise down that you see is useful, but leave the others for later. Sometimes you'll make an assumption before you pull the premises down at all. For now, though, the easiest thing is to start bringing the premises down into your derivation. And so in this case, I'm just going to do that one by one. Notice that I've kind of like offset the second line, the content of the second line. And again, for now, like that's not absolutely crucial, although I think Carnap may freak out if you don't offset. When we get to sub-derivations and some of the other kinds of derivations, we're going to have like derivations in derivations. And then it's going to be really important that the offsetting is there, because that's going to make it clear which line is part of which derivation. For now, though, we only have first order derivations, and so the offsetting is just going to get you in the practice of separating out your the lines of your derivation after the show line. So I've just pulled down that first premise, if P then Q, and then over here on the right hand side, everything after the show line, you should start writing justifications for, and so you don't have to justify a show line, and we'll talk about this later, but basically you can announce that you're going to show anything at any point, because you're not really doing anything. You're just like making a promise, and maybe it's going to turn out that you can't fulfill the promise, but you can always make one. No need to cite anything as justification. Your justification will be whether you're able to pay it off in the end. So you don't justify your show line, but everything after that needs a justification. Again, it's best just for visual reasons to separate that off into a different column. And when you pull down premises, you don't need a number, but you should just write PR. And Carnap likes capitals, so go ahead and just, I think the book may do lowercase. And all of this is just like a convention, and different logical systems you encounter. If you took another logic class, some of these conventions would be really different. But just for the sake of consistency, we're going to stick with capitalizing our justifications so that Carnap will accept them. I still find it a little bit more aesthetically pleasing, but that doesn't matter. PR just means this is a premise. And you'll just keep doing that. In this case, I'm just going to pull down each of the premises, cite PR in each case. Again, you don't need to number the premises, just PR. Once you've pulled down the premises, you then are free to start using your inference rules. Those 4 we just learned, and then later a bunch more that we'll also learn. And then later on after that, there are really useful but subtle rules of inference that you'll actually prove are valid argument forms before you can use them as inference rules. We haven't proved modus ponens other than just giving it an intuitive justification. But in principle, every rule in the logic should be provable in a rigorous method, and we'll do that later. Here, I've started my derivation. Really, I mean, the derivation starts on line 1, but lines 1 through 5 are kind of like freebies, right? Like line 1 is just, here's the conclusion that I'm going to show. Lines 2 through 5 are just, here are all the premises you gave me already. They should just copy what exactly is there. But then line 6, I'm sort of starting to go off on my own here. As you start to venture off from the premises, you should always just keep an eye on what am I trying to do? Don't just like slap inference rules onto premises and just crank things out. Sometimes that's like useful initially to just be like, what can I get from these premises? But for the most part, if you're including it in your derivation, you should have a purpose in mind. And your goal is ultimately to reach not P by relying on the premises and your rules of inference. If you have assumed those premises, you then rely on them and use your valid inference rules and arrive at the conclusion, then what you've done is you've proven that that conclusion validly follows from those premises. Last time we talked about the way in which chaining together valid arguments results in a valid argument that has the first member of the chain as a premise and the last member as a conclusion. That's basically what's going on here. Because we know that principle holds, if we can reach that conclusion in a series of valid steps, we know that those premises validly imply the conclusion. I've cited double negation, and then I've cited line number 5. Why have I done that? Well, I can't really do very much with just the rules that we have with anything before line 5. I could have put 2 tildes on those one of those conditionals, but then I'd be kind of stuck. Like, I wouldn't know where to go. If I look at line 5, I've got S. And then if I look at line 4, I've got if R then not S. And so that should immediately tell me that looks modus tollens E. I can't yet use modus tollens though, because S is not the negation of not S. Not S is the negation of not S. And so simple fix, just appeal to double negation, get not S. And then when I look at, DN is double negation, and then line 5 just says the application of the rule that's relevant is only to line 5. What do you think should come next? Anyone have any thoughts?
Not R.
Yeah, how come?
We do modus totem with line 4 and 6.
Yeah, good. Modus tollens 4, 6. So not R. MT 4 and 6. Does everyone see that? So notice that this is like just a specific instance of that rule. Just like the various specific instances I was running through when I laid out the rules. R here is our box, not S is our circle. Not S is tilde circle, and then not box is tilde R. And you just have to start getting some practice at like spotting these patterns. And sometimes they leap right out at you, but sometimes the more complex they get, the less they leap out at you, and the more you have to sort of do parsing, and like you might have some scratch paper over here and pull the premises over and just start like fiddling with them and thinking like circling similarities, being like, I've got a Q here and a Q here. What if I did this? I apply double negation and then like look at it and then be like, aha, I've got something. I'll doubly negate S and then I'll do a modus tollens. And then you can write that into your derivation. Always justifying as you go. Next up, we're going to do another modus tollens. Once we've got not R there, if we look back at line 3, we've got if Q then R. So once we have not R, we can do another modus tollens and conclude not Q, citing lines 3 and 7. The same move just applied to different lines. Once we have not Q, what should come next? Maggie?
Yeah, not P. How come?
2D.
Right, MT28. This is just a successive application of the very same step, just applying it to different lines in the argument. And you can kind of see, I mean, we did some planning ahead of time, and initially it's going to be useful for you to probably do some like informal planning off to the side and just think through as intuitively as you can, how could one get here? And it's going to be messy, but that'll start to give you like a roadmap in your head as you're actually doing the derivation for like, I know I need to do a lot of modus tollens to get there. And so if I'm just doubly negating and I haven't done any modus tollens, that should tell me like something's going wrong. And conversely, if I've got modus tollens and I'm working my way backwards up to P in order to get that not P, then I'm probably on the right track. And what's nice about this is as long as you're citing valid inference rules and citing the right line numbers, validity is truth preserving, so it chains in that way that we discussed earlier. You're always going to be validly inferring. Every inference you make will be valid, and so whatever you get at the end will be validly inferred from what you started with. If you've cited the right rules, you're not going to worry that you've ended up somehow spreading yourself so thin that the starting point doesn't validly entail the conclusion. It always will. Once you hit the conclusion or the content of your show line, in direct derivations, it's just the exact thing that's there on the show line. When we get to other kinds of derivations, this rule is going to fall away, and you're not just going to straightforwardly be able to always finish once you have reached on a line the content of the show line. But for direct derivations, if you have the content of the show line, which here is not P, alone, and it has to be completely alone, like it can't be embedded in a conditional or have a bunch of additional negations on it, then you have more work to do. It has to be exactly not P, alone on a line with a good justification. Then you know you have shown that the content of that show line follows from those premises. And you then skip a line and don't put anything under here. Just leave it blank, and you'll write DD, and then the line number of wherever you reach that conclusion. And here it's line 9, so it's DD9. Yeah, so you can see premises, and then we've got additional steps, but they're all valid inferences. So once we got to the conclusion, we've proven that those premises validly imply that conclusion. And once you've done your DD9, you can cross out your show line, which just shows I've fulfilled the promise that I made at the beginning. I did show what I said I was going to show. I've derived that conclusion from those premises, and then you box everything underneath to indicate that that is a completed derivation there. Typically, you don't put the box around the show line. You leave that out and just cross out the show part and leave the content there. And that's a completed direct derivation. So like this one is relatively straightforward, but what we just did is prove that we started with an English argument, right? And a version of the argument from evil. We translated it into sentential logic, and we could see that like that argument looked valid in English, but if you were asked on the first day to like prove it, you're like, it just seems like it. But now what we've done is we have translated that into our formal language, and we now have a rigorous system of proof to prove that the argument from evil is actually valid. Of course, validity is the logical part, and if you're doing philosophy, often what you care most about is, are the premises true? Is it true that God would eliminate every evil? Or might a good God, like a good parent, sometimes allow limited amounts of suffering to befall their children in order that some good might come about for their child. That's like where the action is philosophically. But as logicians, we can prove this argument is logically a good one. Yeah, you don't need to know this definition, but all you need to know from this is that when you're asked to validate an argument, you need to do a derivation that has this form, and it's complete whenever you've got a canceled show line, and every non-show line is boxed. Okay, so I'm going to now just run through one on Carnap. Any questions about that? Should be pretty straightforward, right? It's okay if not. If you're like, what? Why are we starting with the conclusion? You can ask. Feel free. There's going to be homework. Some of them are direct derivations, so if you don't feel like conceptually you get it, now's the time to ask. Houston.
My other thing is that how would you decide what order to start moving
Yeah.
your previous argument?
Good. So the answer is that for now, as a practical rule of thumb, I tend to find that it's best with simple direct derivations to just go ahead and bring each of the premises one by one down into your argument. Sometimes what you'll find is that, like, if I bring, this isn't one of them, but sometimes you'll find that, like, visually, if I bring the third premise down on the second line and the first premise down on the third line, I can kind of see how they visually line up, and that's totally fine. You can do that in whatever order you want. You could also bring one premise down, start doing some inferences, and then reach for the other premise when you need it. But you always have to bring it down if you ever use it. So there will be cases where there's idle premises sometimes, but usually you'll need at some point in the argument to rely on one of the premises. I just brought them down sequentially because as we're starting, I think that's the kind of most intuitive way to do it. But as for the logic, you could, in principle, do whatever order you wanted, as long as anything that was relied on was brought explicitly in. Huh? Good question. There was another hand earlier. No? No questions? Okay. So here is Carnap. So you should have all gotten that email and registered. And you should have access to the exercises due this week, a few translations, and then some really straightforward multiple choice on inference rules, just those 4 rules we learned. And then some short answers, I believe, on also on inference rules. Those ones are a little weird. I think that they tell you it's right no matter what, I think. I couldn't figure out how to get the coding right to make it. There aren't many times we have to do short answers in Carnap, and I haven't figured out how to get the feedback on the short answers attuned. But if you write like poop and it turns green, it wasn't actually right. That wasn't the right answer. But we'll go over what was the right answer in class. The others, though, it should only turn green if you actually have the right answer. But those short answers are an exception. And then there's a few direct derivations. They start really simple, and they get a little more complicated as you go. So typically you will start, it'll provide the number 1 for you, so you shouldn't have to number the lines. So what are we going to do here? Does anyone want to suggest how we should start? We're trying to validate this argument. Our conclusion is not W, and then everything before the turnstile is a premise. How should we start?
Show, and not colon, and not W.
Show, not W. Yeah. Good. So one thing I wanted to mention is that you'll see here, instead of a tilde, they're using whatever the name of that is. They're just using, does that have a upside L, sideways L? They're just using that instead of tilde. It means, the meaning of the symbol in the language is precisely the same. And you'll see, that should, I think, be the only departure in Carnap. But if you look at other logic textbooks, instead of arrow, very often, and I hate it, they use horseshoe. I really despise that, but that's actually more common than the arrow. Instead of, we get to conjunction, instead of the caret, often you'll see the ampersand, is that what that's called? This, I can never draw it. Something like that thingy. Yes, this guy. And sometimes you'll just see a dot, actually. And then when we get to biconditional, we're going to use double-sided arrow, which I love. Don't really like triple bar, but people use that sometimes. So like if you go on to read about or think about logic in the future, don't be terrified when you see that there are these other weird symbols. They're all going to have the same logical function. It's just like a notational variant, basically. So we'll start with not W, and we've got colon here. There does need to be a colon, and then a space. I think I don't need the space, but I like to put one. I've set it so that it renders down at the bottom. So as you type, it's going to spit out something that looks a little neater, because especially like when these get more complex, the unrendered version as you're typing looks really messy and it can be hard to track. So I've set it so that it'll spit out something cleaner at the bottom, which should help you. Then you'll just click enter or return. It automatically numbers for you, but make sure to do a space bar. And you should automatically get that little line, which is just telling you that you've opened up a derivation there. Sometimes the first week or so in the first homeworks last year, like a couple of people were like, I know I did it right and it won't accept it. And they're like freaking out. I've been spending 3 hours. I'm like, oh no, it's just because you don't have a space. And so it gets really picky about some of these things. But once you get in the habit of putting the space where it needs to be and putting the colon where it needs to be and so on, it will recognize that your proof is valid. And if you're like, I'm sure I did it right, just double check some of the nitpicky things, and it may switch and be like, oh, now I see that you did it correctly, and it might have just been like a space was wrong. So I'm just going to go ahead and bring down the premises. And arrow, I should mention, I have mine synced up so that a couple of things I'm pressing automatically turn into an arrow, and you can do that if you want to, but I'm doing dash and this. Does that have a name? Less than? No. Greater than. Yeah. Dash and greater than. It'll show up like this without the connection, probably on yours, unless you've synced it up. You can like go into settings in your computer and tell it to automatically replace that with a connected arrow if you want, but Carnap will recognize either one. After that, I'm going to put a colon and PR. And that's my justification. You can see down there at the bottom, it separated it out more clearly. It does need to be separated with a colon. And I'm just going to keep doing that. In each case, just citing PR. And to Houston's point earlier, like, I didn't have to do that. I could have